In this video, we try to see the frequency response of LTI systems. The frequency response is given by the term H omega, and this is basically the Fourier transform of the impulse response HT, that is H omega is equal to Fourier transform of HT. So हमने इसको पहले देखा है convolution property में, that suppose the system has impulse response is equal to HT, and if an input xt is applied to the input of that system, then if the system is LTI system, this convolution gives the output of the system, we denote it by yt. That is yt is equal to xt convolved by ht. Some of the convolutions we have seen already. Now, if you take the convolution property here, we can make use of Fourier transform, and therefore we can get the Fourier transform of yt, which is y omega, which is coming as multiplication of the corresponding individual Fourier transforms of xt and ht, that is x omega into h omega. So we can calculate y omega through the Fourier transform of this convolution, which is there in the convolution property. So the frequency response of LTI systems, how to find out? If you first work out, let us first try to see कि जो LTI systems है उनका description किस तरह से हो सकता है. LTI systems, particularly continuous time LTI systems, they are described by linear constant coefficient differential equations. So यहाँ पर differential equation है, ये first order की differential equation है. Suppose we have dy by dt plus 2yt equal to xt. So this basically describes some input-output relationship of LTI system. So we have described input as xt, output as yt, and this is input-output relationship through some differential equation. So this differential equation denotes or describes LTI system. That for any input, then we can calculate output. So either we can solve it in a classical manner, by the classical method we can also solve, but we can also solve using Laplace transform. And another way is solving the same thing using Fourier transform. So we will now try to explore the Fourier transform to solve this equation. First for finding the frequency response, and then finding some output for certain arbitrary input. So for doing that, इस इक्वेशन से स्टार्ट करते हैं, एंड सपोज आपने इसका फोरियर ट्रांसफॉर्म लिया. So we take the Fourier transform by using the differentiation property. Then because there is a sum, we also use the linearity property. So by using the linearity property and differentiation property, we can take the Fourier transform of this whole equation. So the Fourier transform of this particular term is j omega y omega. Fourier transform of this term is 2y omega, and this term x omega. So we get y omega as common factor. We take 2 plus j omega into y omega. This equation reduces to this form, which is equal to x omega. So now we can solve for y omega divided by x omega, which comes as 1 divided by this term. So 1 divided by 2 plus j omega. Now, according to this property, we call this x omega h omega product as y omega. Therefore, y omega by x omega ratio will be h omega. तो इस तरह से हमने इसका फ्रीक्वेंसी रिस्पॉन्स निकाल लिया यूजिंग फोरियर ट्रांसफॉर्म. फ्रीक्वेंसी रिस्पॉन्स विल डिस्क्राइब how the system behaves with respect to frequency. Suppose I increase omega or decrease omega, that I can plot versus omega, and that will be the description of the frequency response versus omega or versus frequency. Now, suppose we have to take the impulse response. So Impulse response is nothing but Fourier inverse of ht, because ht का Fourier ट्रांसफॉर्म अगर लेते हैं तो h ओमेगा आता है, तो अगर आप Fourier inverse of h ओमेगा लेंगे तो ht आएगा. So this is called impulse response of LTI system. So when we take Fourier inverse of this term 1 by 2 plus j omega, which we have already obtained here, then we obtain, because of the Fourier transform equation that we have seen, this becomes e power minus 2t ut. Because if you take the Fourier transform of this e power minus 2t ut, it is nothing but 1 by 2 plus j omega. So the Fourier inverse of 1 by 2 plus j omega is e power minus 2t ut. So we have determined for this system which was described by the differential equation, first the impulse response and also the frequency response. Now suppose we apply one input e to the power minus t ut, that is xt equal to e to the power minus t ut, to this system described by this differential equation, or described by this ht that we have obtained, or described by frequency response which we have 1 by 2 plus j omega. So these are the different ways of representing the system. Sometimes the system's frequency response may be known, sometimes the impulse response may be known, and we apply some input xt. So we want to find out the output. Suppose we apply xt equal to e to the power minus t ut, and we want to find out the output yt. So either we can do the convolution as usual, जैसा हमने देखा xt को आप convolve भी कर सकते हैं time domain में. So this xt can be convolved with this ht to find out the output. Another way is to use Laplace transform. Another way is to use Fourier transform. So we will use Fourier transform. So the Fourier transform of this yt is nothing but y omega, which is nothing but x omega into x omega according to convolution property. And then we take the Fourier inverse of this y omega to get yt, that is output. So let us use this method. What uses the convolution property of Fourier transform? So we see that because we have xt equal to e to the power minus t ut, therefore x omega is Fourier transform of e to the power minus t ut, and therefore it is 1 by 1 plus j omega. Frequency response h omega is already calculated here, which is 1 by 2 plus j omega. So we multiply it by the frequency response, and therefore this becomes 1 by 1 plus j omega into 1 by 2 plus j omega. It is as good as to see in Laplace transforms term when you try to substitute s equal to j omega over here, or j omega equal to s here. This equation becomes 1 by s plus 1 into s plus 2, like a Laplace transform, with the substitution s equal to j omega. So now we can of course get very easily the partial fraction expansion of this, which is already known to us. So we can expand it using the partial fraction expansion method. So this becomes 1 by s plus 1 minus 1 by s plus 2. So this term, we again put the s value as j omega. So what we get as y omega is equal to 1 by 1 plus j omega minus 1 by 2 plus j omega. So we substitute here s equal to j omega back, and we obtain this equation. Now when we take the Fourier inverse of this y omega, we get e to the power minus t ut corresponding to this, and then e to the power minus 2t ut corresponding to this term. And therefore yt is e to the power minus t minus e to the power minus 2t times ut. हमने ये यहाँ पर देखा कि किस तरह से एक इनपुट हमने अप्लाई किया था इस LTI सिस्टम को, और हमने उसका आउटपुट यूजिंग फोरियर ट्रांसफॉर्म निकाला. फोरियर ट्रांसफॉर्म निकालने के लिए, फोरियर ट्रांसफॉर्म का यूज करने के लिए पहले हमें फ्रीक्वेंसी रिस्पांस पता होना जरूरी है, एंड द फ्रीक्वेंसी रिस्पांस इज नथिंग बट y omega divided by x omega. So y omega by x omega we can solve through taking some Fourier transform of the system's differential equation. It may be first order, it may be second order, whatever. So अगर आपने उस differential equation का Fourier transform लिया, You can solve for y omega by x omega. That will be called as the frequency response. Once frequency response is known, we can take Fourier inverse to get impulse response. We can also solve for some output yt for some arbitrary input. So that we have done here. So thank you for watching this video. This was about Fourier transform of HT, that is impulse response, which is also called frequency response of the LTI system. Thank you.